In this lesson, we will review exponential functions. Here are three graphs of exponential functions, and it's helpful to know what all exponential functions have in common. So looking at these graphs, we see that they all have horizontal asymptotes. And that's a nice distinction to make between exponential and logarithmic functions. So let's just look at characteristics of exponential functions using a palette, and we'll start with this. So the y-intercept is when the x value is 0, and we have 2 to the negative 1. That's 1 over 2. So the y-intercept is 0, 1/2. The x-intercept is when the y value is 0. And to solve an exponential equation, we haven't reviewed logs yet, but we could do log base 2 of 0, log base 2 of 2 to the x minus 1. This reduces to x minus 1. It has a value of x minus 1, but this is undefined. So that means there's no solution, and that means there's no x-intercept for this function. So how do we find out what the asymptote is? Let's look at some points on the graph. All right, 2 to the 0 is 1. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1 over 4. If you have 2 to the negative 2, the negative as you do the reciprocal, and then you square it, so we get 1/4. Here we have 2 to the negative 3, that's reciprocal, and then cube it, so we get 1 over 8. From the table we can see that the y values are getting closer to 0. The asymptote is going to be y equals 0, and we can also see that on the graph. At 0 we'll go to 1/2. At 1 we go to 1. And then it just gets lower over there. With the horizontal asymptote. And then we look at which x values have a point on the graph. All the way to the left there's always a point on the graph, so the domain goes to negative infinity, and the graph continues to the right, so the domain goes to positive infinity. The range, none of these y values have a point on the graph. 0 does not have a point on the graph, but right after 0 there are points, and so we'll use the parentheses on 0, and that excludes 0, but everything right after it is in the range. And pause the video, try this one on your own. 3 to the 0 is 1. 1 minus 1 is 0, so the y-intercept is 0, 0. And we're going to add 1 to both sides, and then we can use log base 3 of both sides. And this value is going to be x. We will review that in the next lesson on logarithms. To what power do you raise 3 to get 1 to 0 power? So that gives us the x-intercept is 0, 0. The asymptote, well, can't see it yet. Let's look at some points. And we have 3 to the negative 2 minus 1. So that'll be 1 over 9 minus 1, negative 8 over 9. 3 to the negative 1 minus 1. 1/3 minus 1 is negative 2/3. 3 to the 0 minus 1 is 0. Oops, that's 3 to the 1 minus 1 is 2. 3 minus 1. 3 squared minus 1 is 8. So it looks like we're getting close to negative 1. If these values are getting closer to negative 1, let's see it in the graph. At negative negative 2 goes almost to negative 1. Negative 2 goes almost to negative 1. Negative 1, a little higher. At 0, we're at 0. And 1 goes to 2. And there's the asymptote. The asymptote of the parent function started at the x-axis, and here we have a vertical translation. So we know the new asymptote is at negative 1, and that helps you graph it more accurately if you know where the asymptote is. So that's at y equals negative 1. The domain is all real numbers, and the range starts at negative 1 and goes to infinity. So again, the y-intercept is when the x is 0. Also remember that e is approximately 2.7, so if we had to use a table, we can just use 2.7 or a calculator. So here we have e to the negative 1, that's a 1 over e plus 2, and that's approximately 2.37. So we'd have 0, 2.37 as the y-intercept. The x-intercept is when the y equals 0. So we'd have negative 2, and the inverse of e to the x is natural log of x. So we're going to do natural log of both sides. This is imaginary. No real solution for the x-intercept, so we have no x-intercept. And earlier we saw a log of 0. Log of 0 is undefined, but log of a negative is imaginary. So if we just have e to the negative 2 minus 1 plus 2, we get 2.05. At negative 1, just using a calculator, 2.135. At 1, we have 3. At 2, 4.71. And plotting these points, trying to see the asymptote. What number are we getting close to? Well, looks like it's going to be 2. We also see a vertical translation of 2, so that they match up, both saying that the asymptote should be at 2. So at -2, we'll go a little above 2. The asymptote is at 2. -1, we go to 2.1. Then we have 0, 2.3, 0, 2.3, 1, 3, 2, 4.7. And the domain is all real numbers. The range starts at 2 and goes to infinity, not including 2. All right, let's go to logarithmic functions. So let's look at some similar graphs to how we started exponential functions. And I'm having all of these go through, they don't all go, but parent functions always go through 1, and they could be steep or shallow. They could also be shifted over, or they could be reflected. But now the difference between logarithmic and exponential is all of these graphs have vertical asymptotes. Exponentials had horizontal asymptotes, so sometimes the graphs could look a little similar, but you just look for the asymptote. And now let's review what this means. It says, to what power do you raise 2 to get 8? Or, find the exponent of 2 that gives you 8. What's the exponent of 2 that equals 8? And we get 3. That's how we can evaluate logarithms. Remember that log of x is the same as log base 10 of x, and log base e of x is the same as natural log of x. And then we have some rules for, I guess they're properties rather than rules. Let's say properties. Properties of logarithms. And if you have log of a product, you can rewrite it as the sum of the logs. If you have the log of a quotient, it can be the difference of the logs. And then when people oversimplify this and they just say addition always goes to multiplication, then they might make this mistake. Or something like that. They just say, oh, every time I see addition, I'll change it to multiplication. Well, that's not true. This is not correct. Also, if we have log of x minus 1, we can't write that as anything either. There's no property for these, and we just leave it as it is. So let's emphasize that we're not looking for properties that have that in it. We're going to leave those out. If there's an exponent, it can be written as the coefficient. And if we want to change the bases, or the base, we can rewrite it as log base 10 of b over log base 10 of a. Or you can do natural log of b over natural log of a, or you can change it to whatever base. So this is base a, base 10, base e. It can be whatever base you want it to be. All right. So here's just a, there are no transformations in this. Let's just see where the shape of the graph comes from. Make the x 0. This says, find the exponent of 4 that gives you a value of 0, and that's undefined. There is no value of 4 that will give you 0. So there's no y-intercept. Let's look for the x-intercept. And when we have a logarithmic equation, we can use an exponential. We can exponentiate, making this and this the exponents of the base. 4 to the 0 is 1, and this says find the exponent of 4 that equals x. This whole parentheses is an exponent of 4. It's an exponent that if you put it on 4, the answer is x, and that's why the answer is x. This cancels, they're inverses, and we just are left with an x. Let's come back to that, and let's look at some good choices for x. So making a table can be challenging just because if I choose 3 and I'm doing find the exponent of 4 that equals 3, that is hard to do without a calculator. So let's choose things like 1/4, 1, and 4. Find the exponent of 4 that gives you 1/4, -1. 4 to the -1 equals 1/4. Find the exponent of 4 that equals 1, 0. Find the exponent of 4 that gives you 4, 1. So 4, 1, 1, 0. 1/4, -1. 1/4, -1. And we can see that it's going to -infinity as x goes to 0. So the asymptote is at x equals 0, and then the domain starts at 0 and goes to infinity. The range is all real numbers. The graph goes all the way down to -infinity, continues up to +infinity. Alright, pause the video and try this one. Substitute as 0, and this says find the exponent of 2 that gives you 0, and that's undefined. We have to be careful that we see that only the x is the argument of log, the 1 is not in the argument of log. So down here, it's not going to be log base 2 of 1. make the y 0, subtract, and we will exponentiate, meaning let's make both sides the exponent of 2, 2 to the negative 1. That equals x. So we see the x-intercept is the half. And let's look at some points, have some good choices for x. Powers of 2, like 1/2, 1 and 2. Find the exponent of 2 that gives you 1/2, and then add 1. Find the exponent of 2 that gives you 1/2. That's negative 1 plus 1. Find the exponent of 2 that gives you 1. The exponent of 2 that gives you 1 is 0, plus 1 is 1. Find the exponent of 2 that gives you 2. That's 1 plus 1 is 2. So we already have that point. We go 1, 1, and 2, 2. The asymptote is at x equals 0. The domain starts at 0, goes to infinity, and the range is all real numbers. We just did that. Let's do this. Base 3. Alright, pause the video and try that one. Y-intercept is when x equals 0. But now we have, find the exponent of 3 that equals 1. The exponent of 3 that equals 1 is 0. So there's the y-intercept. The x-intercept is when the y equals 0. Exponentiate, we get 1 equals x plus 1, x equals 0. So that gives us 0, 0. And let's try some good choices. I know 2 is a good choice because that'll be 3. Let's just stick with that one. Log base 3 of 2 plus 1 is going to be 1. To what power do you raise 3 to get 3? You raise it to the first power. So over 2 up 1. The graph is going like this, but we see that it's hitting the y-axis, so the asymptote is not the y-axis. Looking up here, we can see that this is a translation to the left. So 1 unit, so there's the asymptote. And now we can see the asymptote is at -1. The domain starts at -1 and goes to infinity. The range is all real numbers. And we can just keep doing the same strategy. Remember that ln x is the same as log base e of x, and maybe that would be easier to write it at. If you want to write it like that, you can. Y equals natural log of 0 minus 2. Log of 0 is undefined. Here we have 0 equals natural log of x minus 2. We're going to go plus 2. Exponentiate. Since the base is e, that's what we want to exponentiate with, and this will equal x. And then we have e squared is 7.39 approximately. We could use numbers in terms of e if we didn't have a calculator, and then we can just estimate these values. So natural log of e minus 2. Find the exponent of e that gives you e. That's 1 minus 2 is negative 1. Find the exponent of e that gives you 1, which is 0 minus 2 is negative 2. Find the exponent of e, that's what this says. Find the exponent of e that has a value of 1 over e. So that'll be negative 1 minus 2 is negative 3. And then we can just estimate these values. So if I just estimate this to be about 1/3 and negative 3. About 1/3, go to negative 3. Here we have 1, go to negative 2. 2.7, go to negative 1. 2.7, go to negative 1. Is the asymptote going to be the y-axis? And we see that there was a vertical translation, so that doesn't change the vertical asymptote. So the asymptote is still at x equals 0. The domain starts at 0, goes to infinity. The range goes from negative infinity to infinity. All right, let's stop there.